Moving to the next presentation will be by Lluc Alvarez from the site of Barcelona Supercomputing Center. The topic is an overview of an activity within the Barcelona Supercomputing Center, what is called the Zettascale Lab, that includes a lot of effort around chips, emphasis on the RISC-V instruction set, a lot of prototyping effort, and Lluc personally has been involved also in other ambitious activities. The recently completed e-processor activity. He was the coordinator. That project managed to produce a RISC-V chip at a reasonable level of functionality for an early generation chip. So he has the practical experience and as well as the perspective. Lluc, thank you very much for taking the time to be with us. Get started.
Hello. Thank you very much, Manolis, for the introduction and for the invitation to participate here in this workshop. Yeah, it's been very interesting so far. So today, well, I was invited here to talk about this specific project that we have at BSc, which is called Zettascale Lab. And yeah, before going there, I will put it into a bit of context. One very important bit of context is RISC-V. Obviously, in this room, all of you know RISC-V quite well. I don't need to convince you of its positive aspects. It's open. It's easy to extend, to customize. It has profiles. You can put accelerators, even ad hoc instructions if you want. And yeah, its benefits go in line very well with what we want to do in Europe in this vision of achieving technological independence. It's a great opportunity. It's obviously you don't need to pay for licensing fees, and it's very good for collaborating, and also there's a lot of funding opportunities right now. So yeah, RISC-V is a big piece of this puzzle, and a very important one. And at BSc we have always been very on board with RISC-V. We believe in its benefits. We believe it is the way to go to move forward for European technology. And yeah, we have been very, very active in this field of promoting and using RISC-V in many different projects, leading some of them. And yeah, we are contributing to the community as much as we can as well. So we are pretty much on board with this. So in this direction, you know, BSc, I imagine most of you have participated in the EPI project or in some of the other related projects, right? So you know very well that BSc has been contributing to these European projects. Obviously, well, in the VPU is probably the biggest piece of IP that we are contributing to these projects. And of course, we have participated in these 4 tape-outs that are funded by EU projects. The 2 tape-outs of EPI include the Vitruvius VPU that is developed at BSc. Similarly, in eProcessor, there's an evolution of the VPU that is in the chip. And I had the privilege to coordinate this project, the eProcessor project. And similarly in EU Pilot, we also, well, we contribute with different IPs, the VPU, etc. So that's pretty well known to all of you, probably. What many or some people don't know is that we also have a line of chips and IP that is being developed internally at BSc that may not have that much visibility at the European scope. And this is for instance, the Lagarto family of processors. Okay, so apart from the VPU that is well known and is part of all these European projects, we are developing other RISC-V related IP at BSc. And the Lagarto family, it started back in 2019 with the Lagarto Hun. This is a kind of a microcontroller kind of processor, very, very simple 5-stage in order. But yeah, this was like the starting point, and it evolved into more and more sophisticated designs. So we had another tape out called Divino, which include this Lagarto Hun simple processor, but it also included the VPU. Okay, so this was like a playing ground for starting integrating different the VPU. That was a very early version, obviously, back in that day. But yeah, and this has been evolving. Then we did another tape out, Sargantana, in 2022. We had developed another processor. This one is more elaborated, more complex, more powerful, still in order, 7 stages. This is kind of similar to Ariane, actually, CVA6. But yeah, significant higher frequency and some custom extensions and so on. So yeah, as you see, the tape outs are evolving in technology, in frequency, and so on, and also in the IP. The latest one we have here in the slide is Camaleon. It has Lagarto K, which is an out-of-order core. So this was even yet a third iteration of the Lagarto family, out-of-order core, 11 stages. And it had many, well, not many, 1, 2, 3, 4 accelerators inside the chip. One for, this is hardware support for task-based runtime systems, what we used to do with the OpenMP runtime to manage asynchronous tasks, etc. So hardware support for that. Sauria is a systolic array for AI, post-quantum cryptography accelerator, and WFA is a bioinformatics accelerator. So as you see, we're not doing only VPU, we're doing a diverse set of IPs, including cores, including accelerators, and so on. So I don't know if this is news to you or not. In any case, this is kind of the history that we've been following. Another important thing to note is that we have 4 processors here, and we had 4 in the previous slide. So from 2019 to today, we've done 8 tape outs in 6 years. That's quite a substantial amount of work. And all these previous experiences and so on have led us to this project that is the Barcelona Zettascale Lab project. We call it Zeta for short, okay? So I'm just gonna call it Zeta. The project started in 2022, at the very end of 2022, and it's gonna finish now in roughly 9 months. And the main goal is to build the first BSC-only high-performance multi-core design, including RISC-V out-of-order processor, VPU accelerator, and a high-performance cache hierarchy. One thing that is slightly different quite different to what we do in European projects is that all the physical design and fabrication and the backend work, it's done by Intel. So we collaborate with Intel for doing the fabrication of the chips, okay? And we are doing 2 test chips with Intel foundries. The first one is already done. I will present that and some results, etc. And the second one is about to be, well, we have the RTL hard freeze this month, and hopefully it's going to be fabricated in the shuttle in January 2026. So I'm going to go to that in detail, but Intel is doing a non-negligible part of the work here of the project, okay? Including providing technology-independent IP. And well, the total budget of the project is quite significant, as you see here. It's a large project. It's a large project involving more than 150 people at BSC. This is only BSC people, okay? And the team, obviously, our PI is Mateo Valero. On the hardware side, we have Miquel Morotó as a coordinator, which, by the way, he was initially invited to give this talk and he couldn't attend, so I'm here on his behalf. So yeah, we have architects board with Adrian Cristalos, Manon Sal, Mateo, and Miquel themselves. Then we have high-level simulations with Gen5, with Adrià, RTL design and implementation led by Luis Plana, with the 4 sub-teams out-of-order core, VPU, and core led by me, and integration. And then, of course, verification, FPGA, physical design, and PCB, although these are done in collaboration with Intel. Yeah. And then we have a software part of the project. I'm not going to talk about software a lot because I'm heavily involved here and I don't know about this part so much. It also hasn't been so active yet because we have just received the first tape out. So, but yeah, this is, if you have done any collaboration with BSC on the software side, even in the hardware side as well, you for sure have heard these names. We have Filippo here on the SDBs, Xavi Martorell on the OS, Roger Ferrando compiler, Judith on the tools, Rosa on libraries and frameworks, Marta and Xavi on resource management applications. So it's the usual people that you may have collaborated with at BSC. But yeah, still a huge team, lots of people, and yeah, work across whole stack. Although I'm going to focus more on the hardware side. So these are the timelines of the tape out with a bit more detail. What this shows is something that happens in European projects as well. The timings are very tight. The schedules are crazy tight. We have constant drops. These only show the more relevant ones, but we have more frequent drops of RTL. And then we have the thing on the top is the first tape out. So we have tape out. The RTL freeze was in September last year. The shuttle was in November. We got the chips back just before the RTL freeze of the second tape out. This is something that we would like to. We would like to have more time to receive the first chip, do some analysis, do some characterization, learn from it, right? But the way this project works sometimes is, well, things get squeezed in time. We want to put as much work as we can in very little time, and then these things happen. We have barely no time to learn anything from test chip 1 to test chip 2, and I think that's the case for other projects as well, which is something that we may rethink how to do this. And the same for TC2. Lots of drops, and then we go for tape out, and the chips are back probably by the very end of the project, if not later. So again, very little time to do characterization and support work on top of it. On the software side, we have the usual software stack that we use at BSC. Of course, Extra and Paraver. Also, everything related to OpenMP and the tasking model and their derivatives, higher level like PyComs and so on. NixOS, LLVM, of course AI, and some of the typical resource management workload manager like Slurm, DLB, and so on. All this running on top of Linux with different flavors, and of course the SDB work that well, Filippo's team is not here anymore, but Rave and these other tools that are also used in EPI. So I want to talk a bit about the test chips that we're developing. This is a picture of the SOC, well, a diagram of the SOC. So what you see, I hope you can see this dotted line. This essentially separates what is the BSC VPU subsystem. This is the only box we are developing at BSC. And all these other components are delivered by Intel in a SOC infrastructure called Horse Creek. This is quite nice. We don't have to bother about doing memory controllers and PHYs and PLLs and all this is done. Okay, and it all connects to the CPU subsystem via a very simple AXI, and this facilitates a lot the RTL development and the design of RTL without having to pay attention to all of that. So if your goal is to develop RTL, this is a pretty nice way of doing it. And this is what we're doing with Intel, but there's other companies that are putting up this kind of SOCs for you to tape out more easily. And inside the CPU subsystem, which is what we are doing, essentially this is for the first test chip we have. It's a bit strange, okay? So this started as a pipe cleaner, but then it evolved and we tried to put as much IP as we could into it. So at the end, we ended up with 3 cores. Sargantana is the in-order core, Lagarto K is a out of order, and Lagarto Ox is a superior out of order to Lagarto K. At that time, Lagarto K had this OVI interface connected with the VPU, so that's what we have. And we connected all these to OpenPython. It's an open source cache hierarchy. So we have two L2 private cache, then we have a slice of LLC, and these all connected to routers through a NOC. And then, of course, we have the interfaces to the rest of the SOC. The different taxi interfaces for different things, right? So even if you see 3 tiles here and 3 cores, this is a single core. It's intended to only boot 1 core and use only 1 core at a time. We don't have any time to verify the multi-core part. So it just, putting IP together and trying to demonstrate that it is mature, even if it's only on a single core setup with 3 tiles. So yeah, that was how we approached this first tape out. We have here the layout with the Lagarto Can, the top, and the VPU. Of course, this is a big chunk of the area. Sargantana tile, the Ox tile, the peripherals. All this goes together with the other peripherals, IPs that are part of the SOC, and all this goes into a chip that can be mounted on top of the Hawk Canyon platform provided by Intel, which is it's essentially a board where things are running, right? So yeah, in total we have 3.2 square millimeters for the CPU out of the 15 square millimeters of the whole chip, of the whole die, sorry. We send it for fabrication. We receive the boards without chip. Then we receive the chips 2 months ago, roughly, and we're doing the bring up right now. This is the setup that we have in our lab with the same whole Canyon board, and this is where the chip is. But yeah, we have received 500 chips, 40 Hawk Canyon boards, and some extra boards that were used internally by Intel. We're testing all these. Essentially, most of the additional boards are working. Most of the test chips are working. 466 can boot with any of the 3 processors. That is very good for a pack of 500 chips. And 34 have at least 1 processor not booting, but maybe they can boot from another of the 3 processors. And the same for the boards. They mostly work. Some of them had some problems, but generally speaking, this is working quite well. So it shows the maturity of the IPs and it achieves the goal of this first test chip, which wants to essentially have something functional that we can build on for the second test chip, which is this one. In terms of the SOC, it's very similar. The idea is exactly the same. Intel is providing lots of IP for all these peripherals and so on. The thing is that there is changes and upgrades, right? Especially to improve performance. So there is increased memory bandwidth in this second revision. There is we are targeting a more aggressive technology node, 18A, Intel 18A. And we have more area as well, 4 square millimeters for BSC. We have some sort of access to the PDK, which is kind of, which is very important. And yeah, new interface with the CPU, new address mapping, that also involves obviously changes in our RTL to adapt to these changes. But generally speaking, improving the infrastructure where we put our RTL. And of course, we also improve we also improve the RTL that we put in the CPU subsystem. This is a diagram. It may look simplified, but from what we learned in the first tape out, we said, okay, our best core is Lagarto Ox. Our VPU is something that we want to put, obviously. And of course, we have the caches and the nodes, etc. So we built a real multi-core out of this, out of the best IPs we have, right? Including many optimizations compared to the TC1. So for instance, in the VPU, we have now in-house FPUs, additional instructions, widening, narrowing, plenty of optimizations in the microarchitecture. The same with Lagarto Ox, just a beefier version of the core. It's highly configurable. and lots of optimizations as well in the microarchitecture. And the same in the caches and the NOC, larger caches, more in-flight requests, wider NOCs, optimizations of the internal pipelines of the caches and whatnot to reduce latency. So all these things are from what we learned in TC1 and what we have observed on especially in the FPGA SDB. We have this evolution of the architectural specs, and this is a real multi-core now. This is verified with litmus tests and so on. So it's a real multi-core. And for the ones that are in the DARE project in the pathfinding, you'll see that is a kind of it paves the ways toward that, right? This is these two building blocks connected with a new interface called Barcelona Vector Interface (BVI) is what's gonna derive into the IP that we're putting into there. So yeah, this is pretty much finished. We have the RTL hard freeze in exactly 2 weeks. So as you imagine, the guys in the lab are kind of having a good time, probably, or not so much. But they're definitely very proud of the work, and we are fighting to get it very polished as in the better shape that it can be. So we have a successful chip. Obviously, we don't have any results when it comes to the final physical design or the test chip out yet. Hopefully, I'll be able to follow up. You'll be able to follow up on this in future presentations. But yeah, we are what we observe in the verification phase and so on. It seems pretty solid. So yeah, I wanted to, since this is about experiences and so on, I wanted to comment a bit on this experience of collaborating with Intel. This is, I think, the biggest difference compared to what we usually do in European projects, right? In European projects, you typically have your partner that does the physical design, and then you send it for fabrication to, I don't know, Global Foundries, TSMC, whatever foundry. This is different. This is different because what we're doing with Intel is, well, there's a good thing. It allows us to focus on the RTL. This was the main goal of the project, right? And if we can put the focus on the RTL, and also the physical design team was heavily working in other projects like UPilot and so on. So they didn't really have time to do all this. So yeah, we uploaded to Intel the part of the physical design. So for that, we have very tightly scheduled RTL drops with increasing expectations when it comes to verification, maturity of the code, timing, linting, all these things that the physical design teams request. Yeah. Intel does the synthesis, the physical design, and the basic testings, and we receive detailed reports. And then we kind of see what's going on, what are the results, what to improve, what not, what works, what doesn't, and so on. And that's nice. For us, the RTL people, to see what we have to put in the next iteration, in the next RTL drop. And obviously, Intel also provides boards, as you have seen, and it helps with bring up. So generally speaking, they are in charge of doing many things, and they are doing it well. And yeah, I think if somebody here is an RTL team and they want to do they want to care only about the RTL to do some test chip or whatever, this is a kind of a good formula to avoid complications that are outside of the scope of typical RTL engineers. It also has some drawbacks, of course. Obviously, we don't have control over the physical design part. They are doing it. So sometimes we cannot replicate results. Okay, they gave us a result that to us it doesn't make sense, but we cannot replicate it. So there is this back and forth communication: what makes sense, what doesn't, what's wrong, if it's your fault, if it's my fault, etc. Yeah, when they ask for fixes in timing, in linting, in CDC, in whatever, we can change the RTL, but we cannot test that we're actually fixing. We just need to drop again the RTL, and they come back to us saying, yeah, it's fixed, or maybe not. So the iteration time of fixing things is a bit longer than usual than when you have like a tight relationship with the physical design team. So yeah, at least we have the ability to schedule extra RTL drops if we want to test something specific. Like that is this critical bug, that is this critical timing thing, whatever. We can do RTL drops essentially whenever we want. So that's a good thing, at least that helps alleviating a bit these two previous points. Another thing is that they are very strict with shuttle scans. Maybe it's because they're using them internally in European projects. What we have seen is that if we don't reach this shuttle or this tape out, we have another one in a couple months, maybe, depending on the technology you're using. And it's relatively easy to do a pre-allocation and then cancel it and then come back in a few months. We don't have that here. With Intel, it's way more strict. So yeah, it's kind of different. It's an interesting perspective and experience, and it has positives and negatives, like everything in life. But yeah, it's something to consider. And you are in this if you have this goal of focusing mostly on the RTL and not on the other things. So as a conclusion, Zeta is a large and a very exciting project. It's a big thing at BSC, and there's a lot of people involved. It is already, or it is going to be, hopefully Chip 2 is going to be the first BSC only high performance computing multi-core design. And yeah, we are fabricating 2 chips with Intel with very advanced technology nodes with all the challenges that puts. And yeah, the idea of this project is to have IP and RTL ready for contributing to upcoming EU projects, like DARE in particular, especially the Lagarto and the VPU are hopefully going to be part of the DARE Pathfinder activity. And yeah, as we have just discussed, the collaboration with Intel differs from the typical work plan on EU projects, but it's a different perspective that has good things, and it's an interesting perspective. So that's all I have for today. Thank you very much. Sorry, that's not all I have. I have to show this.
You can even read out the entities. Questions for our speaker? I think you gave us a different flow, as you said, based on what we have experienced in the various projects, and you highlighted pros and cons. I assume the IPs are strictly defined as well, like you have a guarantee from Intel that they don't. So you submit your RTL in a particular format, and they take care of it.
We send it encrypted. Most of the modules are encrypted.
Right.
Yeah.
Okay.
It's everything is well defined. There is a specs. That is all sort of. There's a previous to all the technical work. There's a negotiation of what's going to be there and what not, and a typical specs document that both have to follow.
And there is a learning curve, I assume, right, to be able to cooperate in this type of environment. Is it okay for you to comment a bit on that? I mean, you have seen for example, global foundries path that we usually take. Do you think this is a more streamlined flow?
Yeah, definitely.
Yeah. Okay.
Definitely. So my experience in a processor with global foundries was you give the GDS2 the database and they fabricate it and it comes back. There is a dry run that there's some checking, but that's all the interaction there is essentially. It's very limited interaction. In this case, it's more continued, and yeah. Now it's in a better shape than what it used to be at the very beginning. I think we both have learned on how to communicate and work together. The reports that I was commenting, when we send an RTL drop, they come back with reports. The reports have become much better over time, because at the beginning we were complaining, what do you mean by this? What does this mean? It was not so clear. So that has evolved for the best. And generally speaking, yeah, at the beginning of a partnership, there's always things that don't work well and that you fix along the way, right? It's also important to know that Intel is going. There's been changes in the last years that also has affected this project. They have changed teams, and that's also that has also added some difficulty. But generally speaking, yeah, it has been a productive relationship, and we have both learned from each other on how to work together and collaborate, and yeah, it's been and very tight, a lot of communication.
Okay, I hope the chips turn out to be in top shape.
Hopefully.
Further comments or questions for our speaker? Or from the people on the remote connection? I guess not. Let's thank our speaker again. I think
Thank you very much.
it was an